The views expressed on Skeptically Speaking are not necessarily the views of this station, its affiliates, sponsors, or advertisers.
Bring it on! The skeptics await your letter. Your call, tweet, homing, pigeon, whatever. Desiree Schell gonna raise a little hell, metaphorically that is. Cause we're skeptically speaking.
Hello and welcome to Skeptically Speaking. I'm your host, Desiree Schell. This week, we're going to learn about the elusive subatomic particles known as neutrinos. Guest host Rachelle Saunders will speak to theoretical astrophysicist Dr. Ethan Siegel about the opera experiment and the controversy over data that suggests that neutrinos may be defying our understanding of reality. Or not. After that, I'll speak to Bradley Voytek about peer review, the process that scientists will use to figure out whether those results are accurate. Enjoy the show.
I'm Rachelle Saunders, back again guest hosting today for regular host Desiree Schell, who will return to Skeptically Speaking next week. My guest today is theoretical astrophysicist Dr. Ethan Siegel, graduate of the University of Florida with a PhD in theoretical cosmology. He has been writing about the state of astrophysics and cosmology since January 2008 on his science blog Starts With a Bang, which is now hosted by Science Blogs. Welcome to Skeptically Speaking, Ethan.
Thank you, Rachelle. It's my pleasure to be here.
And I am super excited to have you on the show today because there was recently a lot of media hubbub about a paper published by the team at CERN where subatomic particles seem to be violating one of the cornerstones of the theory of relativity. I am, of course, talking about the faster-than-light neutrino experiments.
There's a collaboration called the Opera Collaboration, and this is a team of just over 100 scientists that are actually working in Italy underneath a mountain called Gran Sasso. And what they do is they generate the initial high-energy particles at CERN, at the big particle accelerator there. What they do is they take these particles, these high-energy protons, and they smash them into a target underground. A target is basically anything made out of normal matter. And what happens when these high-energy protons run into this target is they create a huge number of particles, all different types, because that's what happens when you get up to these very high energies. And what they do is they continue to move forward, obviously, with their forward momentum. And what happens is most of these particles are really, really unstable. The vast majority of them decay in less than a microsecond. And a large number of them decay into something called a muon, which is like a heavy version of an electron, and they also decay into mu neutrinos, which is one of the three varieties of neutrinos that we know of. So what happens is these muons and these neutrinos, they don't decay nearly as quickly, so they continue to move forward, and what they have then is just a huge amount of Earth underground. The Earth will block the muons. The muons can only make it maybe a few meters into the Earth. But from where these muon neutrinos are created at CERN until they get to their destination, where the Opera Collaboration has their detector, that's a journey of 732 kilometers. Neutrinos, believe it or not, can do this all the time. It turns out if you want to have about a 50-50 shot of stopping one of these neutrinos, you actually need something like a light year's worth of lead. So 732 kilometers of Earth is like nothing to these guys. So that's what they do, is they create these very high energy particles by smashing protons into a target. You make these particles that decay. Some of them decay into muon neutrinos, which travel for 732 kilometers underground until they reach the Opera detector. And that's where you detect these neutrinos. Now, the interesting result you brought up is, well, why would we care about this? One of the things that you can do when you send something a very large distance is if you know when these particles were created, you know when these protons first ran into the target to create all the particles that come about from that collision. And you can time when do I detect these particles in the Opera detector 732 kilometers away. You can figure out, well, if I measure the time that these particles traveled for, and I know the distance that they traveled, you can figure out how fast they were moving. And what they've gotten is really interesting. They claim that these particles actually move just about 0.002% faster than the speed of light. So this is the speed of light in vacuum. It's supposed to be this unbreakable speed limit of the universe that all known particles obey. If you're a massless particle, you move at the speed of light. If you have mass, and we believe muon neutrinos do have mass, very small ones, but still non-zero, then you need to move with the speed of light as an upper limit. You can move almost up to, but not quite at the speed of light. But what we observed from this experiment, what the opera team published, is that they actually moved 0.002% faster than the speed of light. Translating that over a 732-kilometer journey, that means they arrived about 60 nanoseconds earlier than they should have.
So I can see a little bit how this is shaking up the community, and it certainly made a splash in media headlines. What were they originally trying to test with this experiment? Were they actually trying to test the speed of neutrinos, or was there something else that they were attempting to test and this was just a sort of a curious result that came up?
You know, there are other things that they're attempting to do. Neutrinos are very interesting particles. If you just take a look at our basic standard understanding of how all the fundamental particles of the universe work, we had expected originally that there would be three types of neutrinos, one for each of the electron-like particles. So there would be an electron neutrino, a muon neutrino, a tau neutrino, and we would expect that they would all be massless, and we would expect that they would all move at the speed of light. What we've discovered over the last few years is that, in fact, these particles appear to have mass, and they can oscillate or transform into one another as they travel over time. And so the main goal of this experiment was to do some neutrino physics, the most interesting thing of which was supposed to be testing neutrino oscillations to see if you can make these muon neutrinos and then in your detector observe signatures of either tau neutrinos or electron neutrinos, which would tell you a little bit about that these neutrinos have transformed from one type into another, and a little bit about how they've transformed from one type into another. So although they have observed that, muon neutrinos appear to be oscillating into tau neutrinos, and that's some very interesting physics, I don't think it has nearly the widespread appeal of the surprising result that these neutrinos actually appear to be moving faster than we expected they would.
So quickly, what is the difference between these three different kinds of neutrinos? Because I had actually not heard that was the original goal of the experiment, to see neutrinos transform into other kinds of neutrinos. And I'd like to know kind of what the difference is between the three.
So there are three different types of what we call heavy charged leptons. You are familiar with only one of them. You are familiar with the electron. It turns out that there are actually two very electron-like particles. One is called the muon and one is called the tau. The muon is about 200 times heavier than the electron is, and it is unstable. It decays after about 2 microseconds. The tau particle is even heavier. The tau particle comes in at about 3,500 times the mass of the electron. The tau lives maybe 1,000,000 times less than even the muon. But when a tau particle decays, or when a mu particle decays, we find that, let's say we have a muon and the muon decays into an electron. Well, you know what the conservation of energy is. And if you measure the original energy of that muon and you measure the final energy of that electron, you find that the electron has less energy than the muon. And this was really surprising. So this was something that they first noted in maybe the 1920s or so. And in 1930, they hypothesized that what would actually be going on is that when you were changing from a muon to an electron, you would actually be producing neutrinos, which you had a very hard time observing, but which would make up for that missing energy. And it took more than 20 years from when the neutrino was proposed to when it was first observed. But since then, they've not only observed what was known as the neutrino, which turned out to be electron neutrinos. But we've observed all three different types of neutrino. The last one was discovered in the early 2000s. We've observed muon neutrinos and we've observed tau neutrinos. So these are, for each type of heavy lepton, we have an electron, a muon, and a tau. We also have a fundamental particle that's a neutrino that's associated with that. So we have an electron neutrino, a muon neutrino, and a tau neutrino.
Fascinating. So let's talk about the results of the OPERA experiment for a minute. Now, since we're talking about really small things that are moving at very fast speeds, I'm having a little bit of trouble kind of comprehending what kind of speed differences we're talking about. How are they measuring the neutrino speeds?
Well, what happens is you can't actually directly measure a neutrino. Like I said, and this is very unfortunate, it makes our lives really difficult. You need about a light year of lead if you want a 50-50 shot of any one neutrino interacting with something. And we don't have a light year's worth of lead. So what we do instead is we take the amount of material that we can fit in a detector, and instead of running one neutrino into it, we run tremendous numbers of neutrinos into it and hope to detect just a few. So what the OPERA experiment did was they took a huge number of protons, and by huge I mean about 10 to the 20, or 1 with 20 zeros after it. And that's how many neutrinos roughly they created that they shot at the OPERA detector. And over the last few years, the OPERA detector has managed to detect about 16,000 of these neutrinos. That means you have about a 1 in 10 to the 16 chance of detecting any one particular neutrino, which, to put it in your terms, is about as likely as you picking the winning numbers to the Powerball lottery. But about 10 minutes before your winning ticket was about to be drawn, you got struck and killed by lightning.
Oh, wow.
Now this doesn't happen very often, and so it goes with the neutrinos is we don't detect them very often, but we make up for this by creating huge numbers of them, so that even though we only detect them extremely rarely, when we make so many of them, we can actually start to build up a substantial number of detections.
You're listening to Skeptically Speaking with Rachelle Saunders, guest hosting today for Desiree Schell. We're talking to Dr. Ethan Siegel about recent headlines claiming neutrinos might travel faster than light. So let's say, just for the moment, that the results are accurate and not due to some experiment or measurement error, and we'll get back to that in a few minutes. But let's say that neutrinos really are traveling faster than light. What does that mean?
One of the things that it means is, first off, our notions of what relativity applies to. Something has to be amiss there. We have, up until this point, thought that the speed limit of every single particle in the universe can move no faster than the speed of light. That if you have no mass, you must move at the speed of light in vacuum. If you have a real mass, you can only move up to, but not exactly at, the speed of light. If this is actually true, if this is actually what's going on, it doesn't mean that you or I can move faster than the speed of light. All that we've observed and learned about protons, neutrons, electrons, all the known common particles, those, as far as we can tell, still have to obey relativity. But neutrinos, this would mean they're something very different from everything we've known up until now. It means that, on average, over this entire journey from where the protons were first fired into this target to where the neutrinos showed up in the detector, it means that, on average, they traveled slightly faster than the speed of light. Now, that doesn't tell you a number of things that you'd want to know. For instance, it doesn't tell you whether they moved slightly faster than the speed of light over the whole journey, or whether they, for instance, jumped at the very beginning at maybe an arbitrarily large speed and then completed the rest of their journey moving at or below the speed of light. That's not something that the experiment was capable of measuring.
I'd like to step back quickly and talk about relativity for just a minute. Can you walk us through why this theory says the speed of light cannot be exceeded?
So this has a lot to do with the conservation of energy. You probably know Einstein's famous formula, E equals mc squared. And that tells you that if you are a particle with mass, the amount of energy it takes to make that particle, or the amount of energy contained in the mass of that particle, is the mass times the speed of light squared. It turns out that when we have a particle that is moving, it's not just equal to mc squared, it's equal to the part of the energy that is associated with mc squared. We call that the rest mass energy of the particle. And then you also have the energy associated with the motion of this particle, what we think of typically as the kinetic energy or the energy of motion of a particle. And in all the observations we've made, in all the tests we've made, we see that as we give more and more and more energy to a particle, arbitrarily large amounts of energy, what happens is, well, its mass doesn't change, and its speed appears to go up to a certain point. But beyond that point, what sort of happens is it seems to get harder and harder and harder to get that extra little bit towards the speed of light. So for instance, at Fermilab, which for a long time was the most powerful proton accelerator in the world, it was able to get particles moving something like 99.99999% the speed of light. But even at that, the total amount of energy that these particles had was maybe only about 1,000 times the energy of a proton at rest. If you could maybe get that up to 10,000 or 100,000 or 1,000,000 or 1,000,000,000 times the rest mass energy of a proton. If you could put all that energy into one proton, you might get some extra 99999s in the 99.999% the speed of light you're traveling, but you'll never actually reach the speed of light. What Einstein's theory of relativity tells us, if it can be applied to a particle, is that it would actually take an infinite amount of energy to accelerate you up to the speed of light. And so that's why we say, if this particle has mass, if it has a real mass and is a real particle as we know these things, then it couldn't possibly be moving faster than the speed of light. So if we find that these particles are moving faster than the speed of light, then they must not be particles as we currently understand them.
You're listening to Skeptically Speaking with Rachelle Saunders, standing in for regular host Desiree Schell, who will be back next week. We're talking about the theory of relativity and how particles that might be traveling faster than the speed of light might make or break it. Now, during my research for this show, I came across Cherenkov radiation, where small particles have already seemingly broken relativity's speed limit. What's going on there?
This is a very clever phenomenon. It's called Cherenkov radiation, and if you go to Google and you put in nuclear reactor, you will see a whole bunch of pictures of nuclear reactors, but a few of them will actually be pictures of glowing blue water. And that is water inside of a nuclear reactor that's used for cooling and steam generation and power. That blue light you see is Cherenkov radiation. I want you to remember that we said no normal particles that we know of can move faster than the speed of light. But that is the speed of light in a vacuum, in completely empty space. You know that if you take a prism and you shine light through it, you can diffract light into a bunch of different colors. The reason that happens is because the speed of light in that prism is actually less than the speed of light in a vacuum. It turns out that water is very good at slowing light down. In a vacuum, the speed of light is somewhere around 300,000 kilometers per second. But in water, that speed goes down to about 230,000 kilometers per second. So if you take this very high energy particle you made that was moving at 80% or 90% or 99% or more the speed of light. Well, it's moving at 99% the speed of light in vacuum. If all of a sudden that particle enters water, it's moving faster than the speed of light in water. It isn't faster than the speed of light or the speed of light in vacuum, but it's faster than the speed of light in that medium. And when you do that, the particle spontaneously starts radiating photons, which are particles of light, in order to slow the particle down. And it will continue to do this until whatever particle you've made, an electron, a proton, is moving slower than the speed of light in that medium. That light you see comes off in a variety of wavelengths, but the visible part is mostly blue. That's why if you Google nuclear reactor and you look at the images page, you will see that blue glow coming from nuclear reactors. An old experiment that was done, and we don't do this anymore because of the incidence of eye and brain cancer, but physicists used to check to see if their particle accelerator was turned on by closing one eyelid, because of course you can't see beams of high energy particles any more than you could see a proton or an electron in air. What they would do is close one eyelid, and they would stick their eye with their closed eyelid into where the beam was supposed to be. And if you started to see blips and flashes of light, that would be Cherenkov light coming from the particle hitting your eyelid and moving faster than the speed of light in your eyelid. And so if you would see those flashes of light, you would know that the beam was on. Of course, physicists don't do this any longer because high energy radiation causes cancer and all sorts of other bad things. But that's the same phenomenon. That's Cherenkov radiation. And it happens whenever you have a particle moving faster than light in a medium.
That is a fantastic story. It's nice to know that health and safety has had impacts in all areas of our lives. So in your original blog post on the faster-than-light neutrino results, you talked about supernova 1987A. How does that fit into all of this?
Every time you have a supernova, you get this huge emission of light all at once. But it turns out that a little bit before that light gets emitted, there is a huge burst of neutrinos that get emitted. Neutrinos, as you might guess, come from nuclear reactions. And when you have a supernova, that is one of the most fantastic instances of nuclear reactions you can imagine in the entire universe. It's basically a whole star collapsing in on itself and undergoing runaway nuclear fusion. When this happens, a vast majority of the energy is carried away in the form of neutrinos. Now, this is really nice because the rest of the energy that gets carried away is mostly in the form of light. But if you create that light in the core of a star, it actually takes some time for that light to reach the surface of the star. Our best estimates is that it would take about a few hours for the light to go from the core where it's created out to the surface of a star and then emitted out into space. But neutrinos don't have this problem. Like we said, neutrinos hardly interact with anything at all. So we expect that when we create these neutrinos, they should be able to pass through the star unimpeded. So this leads to the theory that when you have a supernova explosion, you should see a burst of neutrinos just a few hours before you're able to see the first visible light from that supernova. Well, we have not been fortunate enough to know of a supernova in our own galaxy for more than the last 400 years. But in 1987, one of the nearest satellite galaxies to us, the Large Magellanic Cloud, which is about 165,000 light years away, had a supernova go off in it. And this supernova is known as supernova 1987A because it was the first supernova, the A supernova, observed in 1987. It was the only supernova observed in 1987. But what we did was we saw the light from this arrive. And just a few hours before the light arrived from this supernova, reports from 3 different neutrino detectors across the Earth about 3 hours before detected an unexpected burst of neutrinos. And so what happened is, over this 165,000 light-year path, these neutrinos that were created arrived just 3 hours earlier than the light from this supernova did. If these neutrinos were actually moving at the speeds that the opera collaboration's data suggests they were moving at, what we would have observed is these neutrinos would have arrived more than 4 years early, not 3 hours early. And we had neutrino detectors up and running 4 years prior, and they didn't see a burst of neutrinos.
You are listening to Skeptically Speaking with guest host Rachelle Saunders, keeping the microphone warm for regular host Desiree Schell, who will be back next week. Today we're talking to theoretical astrophysicist Dr. Ethan Siegel about neutrinos that might or might not be traveling faster than the speed of light. And we'll be right back after this.
Skeptically Speaking wants you to question everything. To be a part of the discussion, call and record your question on our listener question line at Speak 73101. That's 773-257-3101. Long-distance charges may apply. Sunday nights at 6 Mountain Time, join our Ustream chat room to listen and ask questions as we record interviews live. Just click the Listen Online button at skepticallyspeaking.com. You can also email your questions and comments to live@skepticallyspeaking.com, or if you're on Twitter, tweet us at Skeptical Radio. To find out where Skeptically Speaking airs near you, to listen to past episodes, or download the weekly podcast, check out our website at skepticallyspeaking.com. While you're there, follow the links to connect with us on our Facebook page, our Twitter feed, or to subscribe to the show in iTunes. And now, back to the show.
Welcome back to Skeptically Speaking. I'm Rachelle Saunders, standing in today for regular Skeptically Speaking host Desiree Schell, who will return next week. Today we're talking with theoretical astrophysicist Dr. Ethan Siegel about recent headlines that small neutrino particles may have been caught moving faster than the speed of light, and what implications that result could have for the theory of relativity. So recently news came out that opera had done some new testing with shorter bursts of neutrinos. What was the reasoning behind that, and what were the results?
Well, there are 3 real possibilities of what could be going on here in addition to the fantastic explanation. And the fantastic explanation is that, yes, these neutrinos are really breaking the speed of light, or at the very least, they're really arriving earlier than we would have expected if they had traveled at or below the speed of light all the way through. And so if we see a phenomenal result like this, one of the things we do as scientists is we immediately say, well, this really flies in the face of what we expect is happening here. So what are the sort of mistakes we could have made along the way that would have caused us to think we see neutrinos moving faster than light if they're really not doing so? Well, one of the things that was a problem is the neutrinos that were created, they weren't created like, okay, we made a neutrino here and we observed that neutrino here. We couldn't make that measurement because what they did, as I told you, is they sent a large pulse of protons at a target, and then they observed much later on a pulse of neutrinos. And this is something that was done many, many times, is they'd send a big pulse of protons, and maybe you'd see one neutrino that arrived at a certain time. And then they'd send another big pulse of protons, and maybe you'd see one neutrino that arrived at a certain time. And you add up all these 16,000 or so neutrinos that you saw, and you say, well, I sent out the protons in this big, wide pulse. It was actually about 10,500 nanoseconds long. And then you say, well, where did I observe my neutrinos arriving? And you try to make that same 10,500 nanosecond long pulse for both the protons you started with and the neutrinos that you wound up with. And so one of the things that could have happened is our detection could have been biased. We could preferentially be seeing the neutrinos that arrived earlier, that had more energy, that arrived towards the front end of that pulse. If that was what was going on, then we would have thought that we saw neutrinos move faster than light, but really we're just seeing more of the earlier neutrinos and less of the later low-energy neutrinos. And so that was one worry. There was a second worry that, well, if you have this big wide pulse, what if your uncertainty, your measurement uncertainty, is actually bigger than 60 nanoseconds? We know you reported it was smaller than 60 nanoseconds. You reported it was something like 8 to 10 nanoseconds. But what if it was actually larger and you just don't know that because your pulse is so wide, because it takes such a long duration of time? So that was a second possibility. And there's a third possibility that, well, maybe we're just not measuring the time correctly. Maybe there's an error somewhere in how we are measuring this time, and maybe our results are just shifted by some amount. So what they did was a new experiment to test for the first two of these, but not to test for the third. That would take a separate independent experiment. So what they tested for was, they said, well, instead of taking this long 10,000 and so nanosecond long pulse, we're going to make very short pulses of protons, just bursts that are maybe only 2 or 3 nanoseconds wide, and we're going to space these out by a long enough amount that we'll know when we see a neutrino which pulse that neutrino is coming from. So that was the second experiment they just did, was they sent out these very short 3 nanosecond pulses one at a time. And most of the pulses that go by, you don't see any neutrinos. But when you do see one, you can point out and say, well, which pulse did this correspond to? And so they would observe the neutrinos and mark down a time and say it correlates with this pulse, and what was the time for that pulse. And they just finished this run and released their data last week. And what they found was, well, actually, you know what? It turns out that we see the same results. We don't see any bias towards the higher energy neutrinos. We don't see a very large broadening in our statistical uncertainty. What we find instead is, again, these neutrinos are arriving about 60 nanoseconds earlier than we thought they should. So there's still that nagging possibility, and this is honestly what most scientists believe is going on, that there is a shift in what they're actually observing, their observing time, as compared to what they claim their observing time is, that they simply haven't accounted for. Everything else looks good. It doesn't look like we can find an obvious error, and it looks like we could rule those two other sources of error, detection bias and statistical broadening or uncertainty in the measurement, we can rule those out. And what we're left with is the option of, well, either neutrinos are actually arriving earlier than they should, or there is some mistake in the experiment that leads them to observe a shorter time of flight than these neutrinos are actually flying for. And so the way to test that is to have a different team with a whole different setup try to measure this independently.
So I have a ton of questions coming in from the chat, and I'm going to try and get to as many as we can.
Fabulous. I'll try to go fast.
No problem. So this question comes from the chat, from Cat Mac.
Since neutrinos are everywhere, how did they identify that the neutrinos detected in Italy were the ones initiated at the experiment?
The way you detect a neutrino is you have a huge block of something for the neutrino to interact with. And hopefully, when you get an interaction, what that means is that you get a neutrino colliding with one of your atomic nuclei. Now, when that happens, you'll get something like a big recoil, and particles will get kicked out. But what you'll be able to reconstruct from that, because you have detectors all around your experiment, is, well, we can trace these particles back that we detected. Where did they come from, and what direction were they coming from, and how much energy did they have? And so in principle, you might see neutrinos that come from the sun, or neutrinos that come from a black hole somewhere in the galaxy, or neutrinos that come from anywhere. But because you can tell the energy and the direction of the neutrino because of how your detector is set up, you can only pay attention to the neutrinos that are coming with the right energy from the direction of the beam created by CERN.
So this question actually comes from Brent, our studio assistant today.
If it turns out that the neutrinos really are traveling faster than the speed of light in the experiment, will we have to throw out or revise any of our theories about the universe, such as the Standard Model or the theory of relativity?
Well, the theory of relativity should still hold for all the other non-neutrino particles. But neutrinos, they're not only already doing something surprising, this would be entirely new. There could be some slightly sensational explanations for it, like perhaps these neutrinos just jump a short distance, a short but finite distance at certain energies, and then they move at the speed of light. That would maybe require a small tweak to the physics we know, but there could be a gargantuan tweak required. Perhaps these neutrinos totally behave in a different fashion above a certain energy, and that would be really interesting. But at this point, we can't distinguish between those possibilities. Theoretically, this becomes a very, very interesting question, and something, as Brent intuits, is definitely going to have to give. My guess is if they are moving faster than the speed of light, it would be a flaw that would have to be corrected, or an unknown that would have to be investigated about the Standard Model rather than about relativity. But that's just my gut instinct on this.
So we actually have a question from Google+. It may be our first Google+ question, from Jim Carver.
If the speed of light is slower than in water, is it possible that in the medium in which the neutrinos were formed, the speed of light is higher than in a vacuum?
So this is something that may be possible. For instance, these neutrinos aren't traveling through empty space. It is conceivable that the neutrinos, as they travel through the Earth, that they observe this Earth as having, well, what we talk about is an index of refraction. That's how we normally talk about the speed of light in a medium. For vacuum, the index of refraction is 1. For pretty much everything we know of, the index of refraction is greater than 1. For instance, in water, it's about 1 1/3. In acrylic, it's about 1.5. It's conceivable that to neutrinos, the Earth looks like something with an index of refraction slightly less than 1. We don't know why that would be. We don't know how that would be. But at this point, I would say that's not an explanation that we could rule out.
So what is the best way for geeks like me and our listeners to keep up with the latest on these experiments and get accurate information?
The best places to go are from the collaborations themselves. The Opera collaboration has pretty much released their results. There are going to be other collaborations working on this. Right now, the Icarus collaboration is testing one particular explanation of faster-than-light neutrinos, and they are also set up underground at Gran Sasso using the same beam from CERN. So they are testing one particular explanation for faster-than-light neutrinos, which is that if they were moving at the claimed speeds, they should exhibit a phenomenon called Cohen-Glashow radiation, which is analogous for neutrinos, what happens to normal particles when they move through a medium where they are traveling faster than light in the medium. If neutrinos are moving faster than the speed of light, they should emit pairs of electrons and anti-electrons, electrons and positrons. And so Icarus is saying, well, if they're moving at these claimed opera speeds, what do we predict should happen? In Japan, there is an experiment underway, I believe it's called T2K, where they are sending neutrinos from a particle accelerator underground to a giant detector in Kamioka, Japan, known as Kamiokande, or perhaps Super Kamiokande today. Will they see neutrinos move faster than light, or will they see that actually neutrinos move at or below the speed of light. The main experiment, though, that should really check this is just starting up now here in the United States. They are sending high-energy particles into a target to make neutrinos at Fermilab, and they are sending the neutrinos underground to a mine in Minnesota. And the MINOS experiment, MINOS, they're going to be coming out with results to see, are their neutrinos moving faster than light or not? And they claim that their experiment should have an accuracy with an uncertainty of only 2 nanoseconds. That would be the smallest uncertainty ever done on an experiment like this.
Just before we leave here, we do sometimes engage in a little speculation on Skeptically Speaking, and so I'm going to ask you now to speculate. What do you think is going on here? Do you think we're on the verge of new science, or do you think this is probably going to turn out to be an experimental or measurement error?
It's extremely hard to make this measurement and make these predictions accurately. What's really gone on in all of this is Opera has had to calculate and theorize and test and all of this. What is the exact distance from where we create these neutrinos to where these neutrinos are observed? They have literally had to carry atomic clocks from where these neutrinos are created to where these neutrinos are being detected and sync them up. They actually had to improve their GPS to get this resolution. They have to account for both special and general relativity for the gravitational field at the locations where they are on Earth and the motion, the rotation of the Earth. So there are very intricate calculations. Now, I trust they've done all of those correctly, and I think that's fair. But what they've basically said is, we think doing all of these calculations, we expected that we would see a shift in our signal of 1,048 nanoseconds. But it didn't differ by 1,048 nanoseconds. When they observed it, it differed by 987 nanoseconds. So that's where your 60 nanosecond difference comes in. That's why they think the neutrinos arrived 60 nanoseconds early. I'm not saying that they did a bad job of this. I think they did really the best job that anyone could be expected to do. However, because of the difficulty associated with this, my gut reaction is that there is a mistake somewhere in there, even if nobody knows where it is. That, to me, is a much smaller reach than to say either relativity or our understanding of elementary particle physics is wrong.
Thank you so much for being here with us.
It was my pleasure. Thank you for having me, Rachelle.
You can follow Dr. Ethan Siegel and his dissection of the faster-than-light neutrino experiments and their results on his blog Starts With a Bang, or by clicking the links on our website at skepticallyspeaking.com. And we'll be right back after this.
On the next episode of Skeptically Speaking, we're discussing the viral menace that makes our lives miserable and has resisted attempts at a cure from the earliest days of medicine. Pharmacist Scott Gavura returns to the show to talk about the common cold. How do colds infect us? What causes their symptoms? And why can't we keep them from coming back? That's next week on Skeptically Speaking, on your local radio station, or online at skepticallyspeaking.com.
You're listening to Skeptically Speaking, and I'm your host, Desiree Schell. I'm here with Bradley Voytek, a postdoctoral fellow in the Department of Neurology at the University of California, San Francisco, where he studies how brain regions work together to give rise to cognition. His secondary research interests involve the process and methods of science itself, such as the role of peer review and the effects of social media on scientific citations. He's an avid science teacher and outreach advocate, and he's spoken at events ranging from elementary schools to TEDx Berkeley to Google Talks and Sci-Fu. Thanks for being here, Brad.
Yeah, thank you for having me.
So let's talk about peer review. What is it exactly?
What peer review should be is the process by which other scientists, generally people who are knowledgeable about whatever specific research is being published on, check over your work to ensure that there are no errors, either logical errors or calculation errors or what have you in the actual research being presented. I think people have a misconception that peer review is a process whereby other scientists will take the data that is being published on and reanalyze it themselves and take a look at the data directly, and that is not the case. So it's very easy for errors to get into the literature if one half of the peer review process, that is the people trying to publish the paper, are being a little bit shady.
Now, what is its purpose?
In theory, I've argued that the purpose of peer review should be that it increases the probability that scientific literature converges upon truth. Mind you, that means that when a paper gets retracted, which is it gets removed from the peer review system because of errors that come to light after the fact, that is actually part of the scientific process. That's a good thing. That means that incorrect knowledge is being culled from the system. But this is a process that occurs at very long timescales, not just within weeks or something like that. So if you see a news article published about some great new finding, and then it turns out 6 months or 2 years or 5 years later that was incorrect and has been retracted from the literature, that's not a problem. That's actually a very good thing, even though the general populace might run with that information as though it's true.
What's the formal process?
Actually, this is kind of cool. I don't think a lot of people have this kind of insight into what the peer review process is like, and I certainly didn't until it happened to me and I started publishing papers and then getting asked to review them.
Right.
So what happens is generally you submit a paper to a journal, and depending on the journal, but most journals, there's an editor, and that editor determines whether or not your work is worthy of being published in their esteemed journal. So you might not actually even get to go into peer review. Generally, you won't. Some of the larger, more prestigious journals, only a small fraction, something like 15-20% of papers that they receive even go to the peer review process. Otherwise, they're just culled at the editor stage. If you do manage to advance onto the peer review process, your paper is sent out to generally 2 or 3 reviewers who are people who are knowledgeable, like I said, in your specific subfield of science. And it should be their goal to try and break down every part of your paper. And then you get comments back from them, and you attempt to address them if they view your paper as being worthy of publishable in that journal as well. It's actually a very long, difficult process. It takes several months, sometimes more than a year. And I have friends in the social sciences where apparently it can take years at times.
Well, now let's step back a moment, because peer review is really a vital part of the scientific process, correct?
Absolutely. I wouldn't argue in any other way.
Right. But you wrote a post about some of the problems with peer review, and you've sort of alluded to them at this point. But and again, it's not peer review itself you take issue with, it's the current process. So you wrote that journals use peer review to provide respectability to the study and its authors. So what exactly is wrong with that?
In theory, nothing is wrong with that. But in practice, what happens is there's a whole culture within science of academic journal prestige. What journal you publish in can make or break a career. At top-tier universities, the Stanfords and the Harvards and, Oxford and Yale and Berkeley and all these kinds of places, if you don't have a paper published in my field in the neurosciences, in one of, I would say, 3 or 4 journals, chances are you're not going to get a job there.
Right.
So if you don't have a paper in Science or Nature or Nature Neuroscience or Neuron or PNAS, which so about like 5 major journals that people have a lot of esteem for, you're probably not going to get a job. You're actually probably not even going to be considered for a job if you don't have one of those. And so, given that kind of pressure, there's a consequence of that, and that is scientists are, on occasion, I would say, more likely to not be as careful about their own research or honest about their own research as they could or should be. And I think you see this a little bit coming out now. There's a website called Retraction Watch, which shows that the number of papers retracted from a journal correlates very highly with that journal's impact factor, which is sort of a surrogate metric of the journal's prestige. And the number of retractions is increasing over time. So people are just sometimes outright fabricating and lying. And of course, that will always happen, probably. But I think when you give this kind of extra pressure to succeed, and get a job and get tenure and things like that, based upon which journals you publish in, I think that just compounds the problem.
But the idea is, now again, the idea is that you get published in a well-respected journal, and that means your science is sound. And that's actually one of the reasons that I'd rather interview on something published in Scientific American, let's say, rather than on something I found on the Science Daily site. Because Science Daily basically provides press releases, for anyone who doesn't know, on new studies. And although they're interesting, I personally don't have the background to tell whether they're actually good science or not. So a scientific journal is not just respectability, it's a filter, right?
Yeah, absolutely. But like I just said, the more quote-unquote respectable a journal is, again, that's measured by its impact factor, usually.
Right.
The more likely it is to have papers retracted, because people are more likely to fabricate data if it means that they're going to get into one of these top-tier journals. So, there's a little bit of give and take, right? There's sort of a small movement now toward open science, and I think this would potentially alleviate a lot of the problems. And that is, like I said, when you review a paper, or if I publish a paper, I don't actually have to give any of the raw data that I collected to anyone. Oftentimes, authors will sign a statement saying that should someone request those data, you will make them available to them. But actually, there was a paper published in PLOS One recently that showed that in a couple of psychology journals where all of the authors had signed this statement, only about half of the authors actually returned or gave the data to the people requesting it, even though that all the authors had signed a statement saying that they would. And then the researchers who requested the data actually went and looked at the papers based upon whether or not people gave them the data or not. And it turns out that the people who didn't give the data had more shoddy statistics in their manuscripts that were published. And so that seems to indicate that openness in your data sharing causes a social pressure that makes you be more honest about the research that you're doing. And I'm not saying that people are necessarily lying, right? I think actual fabrication of data in the sciences or what have you is quite rare. Most people who get into the sciences do it because they love the research that they're doing, right? It's not a high-paying job necessarily,
Right.
usually, right? And so it's usually a labor of love, but it's very easy, I think, for people to not be as rigorous as they could be or should be when you have these extra kinds of pressures.
You're listening to Skeptically Speaking, and I'm talking about peer review with Bradley Voytek, postdoctoral fellow in the Department of Neurology at University of California, San Francisco. This is a really interesting topic to me because a while back during the arsenic-eating bacteria story, peer review was in the spotlight. And it was actually a blogger that started casting doubt on that study, not journals. And there was a ton of discussion around whether bloggers could or should play a role in that formal peer review process. So what do you think about that?
So that blogger is Rosie Redfield, and she actually is one of these very strong adherents to open science. She actually keeps, I believe, an open notebook on her blog. Every day she discusses every aspect of the research that she's doing. I think that's great. I think that's very laudable, and I think more people should be doing that. Practically speaking, it's very difficult, so I think a lot of people don't do it for that reason. And so I think a lot of people have issues in general with the role that blogs should play in peer review because there's a lot of uncertainty about the knowledge of the blogger themselves. Do they know enough about the topic at hand to talk intelligently about it? That said, I think a lot of people conflate peer review with being published in journals. The peer review process as we know it today is relatively unchanged from as it was in the 1650s when peer review first came about. And I think that seems a little bit odd. Technologically, we're much more advanced, and we have the capacity to do more. I think archive.org, which is widely utilized by the computer science and physics communities, I think that's a great model, where people upload their manuscripts to this preprint server, archive.org, and people can get RSS feeds or what have you about their topics of interest, and if a paper piques enough people's interest, then you get this spontaneous peer review that occurs. And so I think the concern a lot of people have is that peer review is scientific memory. It is a historical record of research that has occurred. And when papers are published in a journal, that means that at least someone has looked at it and vetted it to some extent. And I think this is really the crux of the issue that people have with online blog-type peer review, or even a system like archive.org. There's no guarantee that anyone actually looked at the paper.
Right.
And while peer review does have its faults as currently implemented, where sometimes people may not read the paper very carefully, or they may not understand it. I've gotten some ridiculous comments from reviewers who clearly didn't understand basic statistics at some points. That happens, but it's rare. And at least somebody looked at it. The editor looked at it. They sent it to somebody to read who, in theory, should be able to write about it. Me, as the author of that paper, can then tell if the reviewer did read it correctly or not based on their comments. Whereas, a system like archive.org, you can never guarantee that. And I think that's where the issues come in.
Well, you mentioned the social pressures and the career-based pressures of publishing. But one of the big issues that was raised during the arsenic incident was the idea that when an interesting science story comes out, that there is such a race to cover it in mainstream media that the journal-based peer review process can't really keep up. So it does fall to science bloggers to sort through it, at least until the next issue of the journal comes out. I would say bloggers have the immediacy that the media needs, but not the accountability then, correct?
Yeah, what you're talking about is more of a post-peer review process, right? Like you're more talking about bloggers coming in to check the media and make sure that the media then reports on the science accurately, which is also, of course, very important. There's a primary peer review process where knowledgeable people look at the paper and manuscript and try and determine whether or not the authors are logically sound in their thinking. And then there's the post-peer review process, where if the media should happen to pick up on a story, then bloggers can turn around and critique the media's representation of that. So it's almost like peer reviewing of the journalistic reporting on the primary report.
So, okay, we've established that peer review is vital, but the process could maybe use some updating. What are your suggestions?
Oh, that's a much harder question. It's so much easier to critique. I think in an ideal world, if I were going to be very, very naive about it, the perfect system would involve everyone actually depositing all of their raw data as well when you try and publish a scientific paper. The other idea that I like, and this is never going to happen, is something more akin to a GitHub for science, as some people have called it, which would be a version tracking system. A lot of programmers use GitHub to keep their code that they're constantly writing and updating correctly tracked. So, if you have let's say 10 engineers all working on the same piece of code, you can have multiple people working on same aspects of the code simultaneously. You can have some people that don't do anything and don't touch it for a long time and then come back to it. And GitHub is a way of keeping track of all of those changes, merging them cleanly, and constantly updating and improving it. So, if you're creating, let's say, a video game, for example, you might start with the very basics. You have some sort of general physics for the world, but then you start adding details and story and things like that. And you have tons of people working on it at the same time. You have people doing the audio, people doing the visuals, and they can all work on this one giant repository of code until at the end you have a very clean, polished final product. And I think that's a really good analogy in a lot of ways for the scientific process. In a lot of ways, what you should be encouraging is crazy ideas in the sciences. Those crazy ideas, they're all most likely, the majority of them are going to be totally wrong. And that's fine. In the sciences, we advanced by learning from our failures. And, you can have people check over where all these incorrect pieces of information are. You can have a lot of people working on the same thing at the same time and advance them. And so, if I had some sort of, like I said, GitHub for science, you could have multiple people working on the same data set at the same time. My big beef right now with the way that peer review process works is your goal is to publish a paper. And a paper is a biased snapshot of the author's interpretation of their data as filtered through the lens of their own ability. So if I only know how to do 3 techniques, I will use those 3 techniques to analyze my data. But there might be 45 other ways of analyzing the data that are better. But because I don't know how to do that, you lose a lot of valuable information. And so if you had some sort of distributed scientific process like that, I think we would all be the better for it. But as it is right now, you get these static snapshots.
Open source science. I like that, sir.
Thanks. It's never going to happen.
Optimism! Brad, thanks very much for being here.
Thank you so much, Desiree.
You can find a link to Bradley Voytek's work on our site at skepticallyspeaking.com. While you're there, click the links to our Facebook page, to Twitter, or to iTunes, where you can download past episodes, subscribe to the show, or leave a review. Thanks for listening, and we'll see you next week on Skeptically Speaking.
Bring it on, the skeptics await your letter. Your call, tweet, homing, pigeon, whatever. Desiree Schell gonna raise a little hell, metaphorically that is. 'Cause we're skeptically speaking.